Okay, welcome back to Information Storage and Retrieval. Today, we're going to get into another form of tolerant input, and that has to do with spelling and phonetic corrections, or generally, error correction. So, in general, tolerant input is, if you recall, the idea that we want to make the things that the user inputs into our system a little more flexible, whether that's intentional, like we talked about last time with wildcards, so letting the user give an underspecified term, and so that our system can go and search a little more broadly using partial matching, right? So this allows, if the user isn't quite sure about every letter of the word, they can, they can identify that and use these systems of wildcards to help find those things. In the same spirit, sometimes the user doesn't know that they don't know every letter of the word, and they try to search it anyway. And this is about human error and correcting it. So, human error. We all do this. No one is immune. Some of us like to pretend that we can be immune, but let me tell you, your nervous system just isn't like that. You will make errors, and increasingly, you will make more and more errors as we use more and more touch screens. We use more and more systems that are a little bit, they're just not the best feedback for our little thumbs, or giant thumbs in my case, which actually is the problem. So we have other systems in place like autocorrect. We have systems like spell check, right, when you're composing something. And we even, we self-check ourselves, right? So we will put a little asterisk and say, this is what I actually meant. So we are prone to this, and this happens quite a lot. It's just a part of the nature of all users. A quick aside, why would we correct them at all, right? Would it be easier just to make users correct their own errors, right? Hey, why do we want to let these jerks just be lazy and type things? I'll tell you, 3 reasons that have all evolved together over the course of technological development. And that is, first, these errors are going to happen more and more. Touchscreens are ubiquitous. They're smaller and smaller. And there's just a variety of ways that we input things. Sometimes we're using speech to text. Even that has its issues. And sometimes we need a way to, bridge that gap. On top of that, because these errors have been happening more and more, we've developed a lot of ways to computationally identify them and offer alternatives, right? So we can do this, right? So these things happen. We can do this. And on top of that, users are very sensitive to time wasting. So we've all become a little bit accustomed to some level of error correction. So if we're not doing this to some extent, it can really make our system seem cumbersome. We've evolved beyond saying, oh no, the user is responsible for clean and precise inputs. That's just not the way things work anymore. So the reason we would get into this is we want to make our system smooth this stuff over, because ultimately these errors aren't typically interesting. It's a small typo, a stupid little flub that often we know we can compute the correct word. Not always. Sometimes there's a disambiguation involved where we have to figure it out. But ultimately, it's useful for the user because of all these factors. So let's do some error correction. Lots of reasons we make these errors, as I just discussed. Basic typos. You may have remembered the word wrong, right? You may have always thought it was spelled a different way, or you've only ever heard the word, that kind of stuff. And we want to help our users, if we choose to implement all these tools, we want to help our users skip the tedious steps of all this self-correction and get on with their search, right? So let's look at this example. Another lady singer, Janelle Monáe. She's got not the worst name, like in terms of being able to remember the exact letters of this name, not the worst you've ever seen, right? But there's some hang-ups here. There's some errors you might make. There's a lot of L's. It's got this sort of French pastiche to it. We can make this would be a ripe name for getting one or two letters, right? So we're going to talk about two kinds of correction today. Spelling correction, where you may omit a letter, you may change a letter, right? And the system is still able to suggest an alternative. How did Google do that? Is it magic? Hope you know by now the answer is never yes to that question. The answer is there is a computational process that they engage in to figure out what's the most likely thing that this person meant to type. There's also phonetic correction, where I might be entering words and letters together that actually don't really map well to the actual letters, but they sound the same. Janelle Monet, right? This is a very common one. But Google can still fix it. Interesting. How do they do it? That's what we'll talk about today. So the two versions we'll cover. I'll tell you right now, spelling correction has a lot of interesting steps, all computational in nature, that we'll talk about. To convert something like Jamel Monet into Janelle Monet, right? Or phonetic correction, which is a little lighter, but still interesting to talk about. So Janelle Monet becomes Janelle Monet, right? So let's talk about each of these in turn. We got a lot of technical details this time around, just to prime your pump. There's a lot of processes we'll be getting into, and they're all quite useful, and some of them have familiar components, but some of them are a little new, sort of like common themes you'll see in text processing, natural language processing type stuff in the future. So get ready to learn some broadly applicable stuff. Spelling correction. Okay, another quick intro here. Sometimes the user makes a simple, stupid type, right? Happens often. We get used to typing quickly. We do all kinds of things in our phones that are a mess, and we can help, is the point. And by way of another quick demonstration, here are some actual recorded errors that are recorded by search engines like Google for Britney Spears, right? I know it's sort of more and more antiquated pop idol, just bear with my 30-year-old self. So, Britney Spears, that's the word we're looking for. There's Britian Spears, Britney's Spears, some people type, Brandy Spears, some people type, Britney Spears, some people type. And we can laugh, a little bit, but ultimately, we all know what these people are looking for, right? That we know, even though it says Brandy Spears, how often are we going to come across They probably meant Britney. They probably meant something that has a lot of the same letters, that are connected, that they're close together, that kind of stuff. Also consider that sometimes you're working from a different culture where you might have different phonemes, right? You might speak a language that isn't used to BRs, but has a lot more PRs, right? We want to enable search for people who are, a little bit beyond their scope in terms of language. It's just a useful thing to do for your users. So, let's break down the spelling correction process, as we will do it algorithmically. So, the basic process is we will start with a bad term, right? So this is the kind of term that maybe we discover doesn't have any matches whatsoever, right? First, what we'll do is we will find a reasonable set of nearby terms. So things like carrot, taro, cart, cat, dog, maybe not so much. There with a method of determining which of these is sort of in the reasonable set of likely replacements, right? Pardon. Then we would compute the nearest term among those. Bloop. And these are all actually fairly close according to the way we'll define it. And so ultimately we would have to then also break ties. So this is the step. These are the steps. I'll tell you now, there's very few steps in break ties. There's lots of steps in finding reasonable nearby terms. So here are the processes that we will learn today. There's a handful of them that are all useful. So first is k-gram overlap. Thankfully, we're seeing our old friend k-grams again. We will learn how to compute something called the Jacquard coefficient. This is a method of really determining how well two sets of things overlap in a general sense. That's what it is. But we can use that sort of set theory type stuff right here for good measure, literally good measure. And then we'll also learn minimum edit distance. This is a sort of a lexical processing skill that lets you determine how close together are two words in terms of their lexical features and characters. So let's get into the first step. I need to find, for the word carrot, I need to find a set of reasonable nearby terms. So how do we do that? We think about the word board, B-O-R-D. That's not a word, right? The question is, what terms are close enough to spell correct to, right? We have to determine a set of close enough terms. Two tools that we'll bring in. K-gram overlap. So this is to select a baseline set of terms. We can do this using our k-gram term index. And then also computing a Jacquard coefficient between the possible terms and determining which ones are most likely. You'll know what that means after we cover what that does exactly. But these are the purposes. So k-gram overlap basically to select a few terms, and then the Jacquard coefficient will help us really pin down which ones. So what is k-gram overlap? Remember that the goal is to find out what are the closest terms to our bad query, right? We have the word board, right? And what's nice is that we can use the k-gram term index to go and find a set of words that has some minimum overlap to just say, hey, which ones of these would even be close, right? So let's say we want to set a minimum overlap of 2 for the word board, right? Well, we have BO appears in lots of words, of course, right? This is our bigram term index. So BO points to a board, about, boardroom, border, all that, right? Or points to some of the same words, right? So border, lord, morbid, sorted, blah, blah. RD points to some of the same words, but also different ones, right? So the idea being, we're only going to include something in this set of words to be considered as an alternative if they satisfy a minimum of 2. In this case, we've set it at 2. So let's look at each term and see, does it actually satisfy that? BO, well, a board works, about works, boardroom works, border. Lord doesn't, morbid doesn't, sorted doesn't, arted doesn't. Okay, good. So BO gives us those as words that contain one of the bigrams from our bad query of board. We can also check, we can continue to check or now, right? So or appears in border, lord, morbid, sorted, not ardent. Okay, cool. And then we can look for the RD. So aboard, good. Ardent, good. Boardroom, good. And border, good. If we want to make sure that only include words that have a sufficient overlap, we would pick out, for the bad term board, we might pick out a board, we would pick out boardroom, and we would pick out border, right? We have an overlap minimum of 2, and those are the only ones that satisfy in this case. So we can specify this minimum overlap. Larger Ks are better, but that scales rapidly. That makes it so that we have to. The issue is that lower overlaps give more recall. They're less stringent, right? So if I only require 1 bigram of all the words to be considered, then that's going to produce a lot of options that are going to kind of waste our time, right? But if we have a really high overlap, well, that's nice and precise, but that also makes it so that we're maybe not likely to find a good replacement because the user could have kind of butchered the word, right? So we want the set of terms that has the highest overlap, not just the minimum. But the issue is that if we're just doing all this based on simple overlap, it doesn't really get us all the way there. So think about what we had before. Board is probably not going to want to be connected to boardroom. Boardroom is so much longer. There's so much opportunity for the bigrams of board to fit into that word, but they're not, it's not mutual, right? Boardroom has a whole lot more going on, and it seems unlikely that the user would have made this error. They would sort of know that they were typing a longer word. They wouldn't type B-O-R-D to try and get boardroom. The question is, how do we detect this mathematically? Makes some sense. We're talking about trying to see what's the overall overlap mutual between these two. This brings us into the method of calculating the overlap of 2 sets, the Jacquard's coefficient. Oh joy. So this one, I'm gonna try to take it slow. It's an important concept for all understanding of sets. We're working a lot with sets, right? So understanding what is the Jacquard coefficient value between 2 sets. So the Jacquard coefficient. It's always between 0 and 1. And the idea is, can I measure the similarity of 2 sets? And what it does is it considers the proportion of the matches, right? But also the size of the sets. So let's look at some examples. Here's the none overlap, right? This is technically a 0. I just have it sort of on the left, right? There is no overlap between these 2 sets. These 2 sets would have a Jacquard coefficient of 0. 0, pardon. Then there's the basic poor overlap. Okay, they're not quite overlapping all that much, right? We can carry on forward, right? So a good overlap would be quite a lot of them overlap, right? And remember, just to couch this a little better, we're thinking in terms of bigrams between 2 words, right? Perfect overlap would be all of the members of one set belong to all of the members of the other set. That's great. This could be literally the exact same word, in which case we probably wouldn't be spell correcting. Or it could be the same word but totally jumbled, all the same letter clusters but kind of jumbled up, right? Those would have very high Jacquard coefficients. They are a perfect overlap. The 2 sets are completely overlapping. But what about the sizes, right? These are all for equal size sets that I've shown you here. Well, what would a larger set and a smaller set be like? Well, something that might have complete k-gram overlap, but not good Jacquard coefficients would be like this poor matching. Right? This, the pink set, is a whole lot larger than the blue set, even though the blue set has complete k-gram overlap with the other set, right? It's not a mutual overlap. Whereas if the larger set was a little bit smaller, it would have a pretty good overlap, comparatively. So I hope this is making sense for, the difference between board and boardroom would be a poor match, whereas board and a board might be a good match. So, how do we calculate this? Well, thankfully we can rely on some things we've already touched on before. because the exact definition, the broad definition of the Jaccard coefficient is just this. It is the size of the intersection of two sets divided by the size of the union of two sets. Interesting. Nice that we're able to pull on some things that are sort of already baked in, and that's all we have to do. So if we do that division, the idea is that the closer that these two values are, the better the fit is. How can we do that mathematically? Well, it's kind of nice we can rely on just three pieces of information. We don't have to necessarily calculate the union as long as we're going to calculate the intersection size. So how can we do that? Well, the intersection is, remember, the overlapping parts, the overlapping number of k-grams, okay, divided by, how else can we get this? We can take the size of all of set A, add that to the size of all of set B. Now, that's good. That's almost the union. That's like the size of both sets. But we're kind of failing to account for the fact that we counted all of the intersecting pieces twice. So we subtract off the intersection again. This is it. I know that calculating coefficients is a little bit kind of like, oh God, get into math. But this is all it is. It's just the intersection of two sets divided by the union of two sets in terms of size. So let's do that with some k-grams. Okay. The overlap, I'm going to call the number of k-grams in common between the query and the term. The query, I'm going to call the number of k-grams in the query, and the term, I'm going to call the number of k-grams in the term. Remembering that this is a bad query and a term that is a candidate for being a good fit. So, board, B-O-R-D, right? That is three pieces. B-O-R and R-D. Sorry, B-O-O-R and R-D. I've already colored two of them as overlap because we already know that they're also in boardroom, right? Whereas boardroom is the term that we're looking for. That has B-O and R-D, but it also has O-A, A-R, D-R, R-O, O-O, and O-M. That's a lot of stuff. How can we prove mathematically that this is a pretty bad fit between these two words? We can say the intersection, the overlap, is 2. There's 2 pieces in common. The size of board in terms of its k-grams and the size of boardroom in terms of its k-grams gets us 0.22. That's a poor fit. So, I mean, it's a poor fit to our eyes. How do we decide that it's a poor fit? Well, we would set some kind of cutoff to say, hey, these need to be at least like 80% similar for these things to kind of feel right. So that's how we use this. We find terms with the k-gram overlap, the basic terms of some simple cutoffs. Like I only want a few terms. I only want terms that have a minimum number of k-grams in common. And then I'll go through with the Jaccard coefficient and prune that list down to an even better set. Typically, you'd specify it 80% is all right. But you can also experiment with that number, right? Ultimately, if you build a system that implements the Jaccard coefficient, we can tweak that number. Maybe it works better or worse for some particular set of data. So recapping that step, so this is spelling correction, and specifically selecting a set of nearby terms, right? This is that first step in the overall spelling correction process. So the first thing we do is we get the k-gram overlap. We say, hey, give me some minimum possible options for the replacements I'm going to do. And then I use the Jaccard coefficient to prune that list down. But we do need to specify in both cases some sort of k-gram overlap and a Jaccard coefficient, or rather Jaccard threshold. But the main idea being, for these different thresholds, these are sort of the knobs you can twist to, maybe you only want a very kind of precise set of replacements. You don't want to offer a whole lot of possible candidates for spelling correction. You want a tighter set, so you could increase these thresholds. Again, this is the kind of thing you would tweak, adjust as you built a system out using this tool. Okay, next step of spelling correction. We've got a set of reasonable terms now. We went through all the steps. We consulted our K-gram term index to find some good overlapping terms using K-gram overlap. And then we also did some extra filtering on that to find only things that have actual good overlap for a Jacquard coefficient analysis. So now we can actually move on to another interesting process where we will compute the nearest term. Okay, what does it mean to have words that are near each other? We want to find the closest word to autocorrect, right? To spelling suggest. And to do that, we need some way to characterize the distance between two strings. That's a strange thought, right? Strings are typically not thought of as, distance is numerical. Distance is about distance. It's a number of feet away from something. It's a number of units of measure away from something. And text is not typically thought of in terms of numerical values. But we can actually take a look at distance in text. So, edit distance, or Levenshtein distance. It's a way of expressing the distance between two strings in terms of the number of edit operations it would take to convert one string into another. There are 3 options for an edit operation in this world, in this Levenshtein distance world. There's insert. You can put a letter into a string in a certain spot. There is delete. You can remove a letter from a string in a certain spot, or you can replace a letter in the string. Let's look at some of this. Cat. So if I wanted to convert cat to car, that's an edit distance of 1. We did one replacement operation. We replaced the letter T with the letter R. If I wanted to turn cat into dog, I'd have to do a lot more work, right? There's nothing in common between these two. At least they're the same length. That's kind of nice. But we got cat. I'll replace the C with a D. I'll replace the A with an O. I'll replace the T with a G. Okay, at a distance of 3. Okay, what about cat to cart? Well, that would be just 1, an insert operation. Cat to cart at a distance of 1. So again, insert operations mean you can put one new letter anywhere. Cat can become cart. Cool. And in a single step. Delete operations would be remove any letter, so cat can become at in a single step. And then replace means change one letter to another. Cat can become caught in a single step. Let's noodle with an example. So, if I wanted to turn capital into catapult, we're working with a lot of stuff now. There's a lot of directions you could go here. Let's just walk this particular direction. We have a few options available. We can convert the P to a T and turn it into catatul. We can convert the I to an A, turning it into catatul. Convert the T to a P, catapul. Convert the A to a U, catapult, and then add a T on the end, catapult. Edit distance of 5. The way we did it, right? So it's a complex process. You can see that this is not necessarily straightforward. We could make a lot of different decisions. The idea is trying to find where are things in common between these words and what is the best way to get from one destination to another. And that's why we talk about the minimum edit distance. So as you saw, there's more than one path, right? we can do a lot of stupid stuff in to turn cat into car. We could go cat, cart, cat, cart, cat, cat, car, right? That is technically a valid process in the edit distance family, right? But we're looking for the minimum edit distance, cat to car, a single step of a replacement operation. So there are lots of ways to calculate this, and again, this is the kind of thing that it's one step too deep for us to cover in depth in the course, I believe. But rest assured, there are methods to say, I have two strings, and I would like to find the minimum edit distance, please. So the thing you need to know about them, though, is that calculating edit distances in this way and finding the minimum distance between two terms is expensive. You have to do a lot of, you're sort of checking tables and looking at examples and paths, and there's a whole lot of weird processing going on under the hood. And again, we may revisit this depending on what kind of material we get through in the semester, but the idea is that you can tell that there's a lot of possible paths, and trying to sort through all of them to figure out the minimum path between one word to another word, that's going to cost you, right? So that's why we went through all the effort of doing the k-gram overlap, which was nice and clean because we already had our index available to get some terms. And then doing the Jacquard coefficient, narrowing down even further, gives us a nice small set of terms to work the edit distance formula on. So another interesting wrinkle in the edit distance idea is that you don't necessarily need all of your edits to be weighed the same, right? It seems maybe like it should cost a little less to replace an A with an O. They're both vowel sounds. An A to an X, well, an X is kind of that's one of the hardest, most complex consonants. You're probably not going to mistake that for an A, right? When you are typing, when you're making these errors. So the question ends up being, are there, based on what we know about the way people are making the errors, can we make some things seem a little bit less costly and more likely? So vowels could be interchangeable, right? Another rule of thumb is that the first letter, we almost always get that right. We almost always know the first letter. So don't screw with the first letter. If the first letter is changed, that should be an extremely high cost. Unless maybe it's a consonant to a consonant, like a C to a K, a very common error. So also an interesting other way you can tackle this is that keyboard adjacent letters are probably likely to be error prone, right? A versus S versus instead of A versus P, right? P is at the total opposite end of the keyboard, whereas S is right next to A. Guaranteed you bump into these ones a lot in your texting. Certain D and F words get mixed up pretty quickly, huh? So that's just an idea. It's an important idea on how these systems interface with the ways that humans actually make the errors. So on top of finding minimum edit distances generally to say, hey, what's the nearest word, we can add extra little helping weights to say, okay, that's actually not a far distance because keyboards are laid out the way they are, and things like that. So that's step 2. Now on to step 3, break the ties. So we have found the reasonable terms, we have winnowed them down, and we have computed the nearest term. If we end up with two terms with identical edit distances, we have to break the tie. So, carrot is just as close to carrot as it is to taro. Now, again, if we use the weighted edit distance, we might not end up with that, right? The first letter being preserved would be meaningful. But in many cases, you will end up in this situation. So how do you do it? Well, it's kind of dumb. You could just return the results for both, offer both of these words as an option. You could also return only the most commonly used term. If you've been keeping track of how often your terms appear in your data set, in your collection, right? When you go through the indexing process, you might be keeping track of how common a term is. So then, well, that's quite nice. That makes it so that we can say, this is the more common word. I'll err on that side. And if your system is really clever, you might be keeping track of what people actually search. So if people search carrot more often than taro, you're probably going to return carrot more often. All of these are valid. All of these work. They're kind of straightforward. There's not a complex algorithm involved. It's just about what's the tiebreaker? What do you use as the tiebreaker? So that's it. We have gone from a basic, we have a bad term come in, a term that doesn't turn up any results. We can then say, hey, I'm going to go find some reasonable terms. I'm going to narrow them down. I'm going to measure the distance to my word, and then I'm going to break the ties. Here's your word. I think you meant carrot. That's how we get our original situation, and how Google can turn Jamel Monet into Janelle Monet. So, to recap, the whole process is we're going to take a bad query, run it through the kgram term index to find a set of terms with the most overlap, use the Jacquard coefficient between those two words, also in terms of their kgrams, to prune that list, and then compute the minimum edit distance between the bad term and all of the overlapping potential terms, break ties using, say, search frequency, and then that's a good potential word for autocorrection to offer, right? Now, this is an expensive process. It's a great tool to offer to your user. It's a great thing to give them on the side. And it's powerful, right? But it's costly. So when do we do it? There's a pretty simple policy. There's a good rule of thumb. Do it reactively. When there's no results, or maybe an incredibly small number of results compared to what you might expect a user would want. But erring more towards no, right? We're talking only very few if it's a very large data set. If your search term comes up with nothing, it might be good to double back and say, we'll go and look for an alternative to each of these words. Now, another question is, how do you actually present this to the user? You can automatically present the corrected version of it, but that can be really confusing. You don't want to just give them a different search term without telling them, hey, I intervened and corrected your dumb query into this slightly more plausible query. So you want to give the user something to understand what's happening. Like Google does, did you mean? ? But you could also just say, showing results for your exact term, this alternative, and this other alternative, whatever. So depends on what you're after here. So one other kind of spelling correction that we should mention is it's not a different process. It's the same. You would still run the same spelling correction process, but there's this kind of tricky thing where isolated terms make sense, right? Correcting for each term, karat to carrot, well, that makes sense, right? But there are times when somebody has spelled a word correctly, but it's bad in context. So running from eats to west, we could tell immediately that that's stupid. That's not a meaningful search, right? This would be a context-sensitive correction. So this would be, again, very reactive. You would want to use this very reactively, and you would only use it on phrases, right? So if every individual word in the phrase is correct, the problem is that the spelling correction algorithm is going to return something that is that word, right? even if you just ran it on each one of these terms. It's going to say, hey, I found the same word again, because it's exactly overlaps and it's zero distance, right? So you would need to come up with a fallback, a different function to say, hey, this phrase returned nothing. So I'm going to go through each term and run the same search again, but replacing each term with its nearest neighbor. So rubbing from east to west, well, it's probably still stupid. Running form east to west, and then running from east to west. Oh, that's going to return a million results, right? And then running from east to best. Well, that's still goofy. So that's spelling correction. You now have an understanding, I hope, of how the algorithms work to produce spelling correction suggestions. As we said, it's quite involved, right? But it introduces a lot of really good tools, understanding how to process numerically process words and terms and strings. We're looking at things like k-gram overlap, Jacquard coefficients, minimum edit distance, good stuff. And it's all in service of our primary idea, which is to connect. There's an issue of the user has an information need in their head, but the search query is whatever they write. So we can help algorithmically solve some of these stupid common mistakes to help more quickly connect, hey, I think your search query should be closer to this, your actual information need. That's my guess. That's what your system comes in and says. So this is a really cool system to employ. It's not necessarily critical for every information retrieval system. You don't necessarily need to go through all these steps, but it's quite useful, and it can be flexible. There's a lot of knobs you can tweak to decide when, how, to what extent you employ these things. So very good to understand. Also just good to understand this as you type during your day, right? You'll have a better intuition on how these things are working under the hood. That's my hope. Now, before we break, I'm going to talk about a different kind of correction. So this is phonetic correction. And I think these are quite kind of fun, actually. So sometimes a user has only really ever heard a word, right? How often does that happen to you? I've only ever heard a term, I go to type it, and then my friend looking over my shoulder is like, God, what are you doing? So what we can do to help correct these kinds of errors is we can build something called a Soundex term index. Soundex is this method of, it's an algorithm to convert a string of text into this sort of phonetic encoding. So the idea is that the codes, it turns terms into this sort of reduced sonic form by what sounds are present in the word as opposed to what letters are present. So what's the basic algorithm? We can convert every term into a 4-character reduced form. Okay, that's a weird thought. Let's look at it. You will always keep the first letter, because as we've said before, it makes sense to have letters that are similar, right? Next step, you will change all the vowels and even the soft consonants like W and H and Y, make those a 0. Those are all lumped together in the same category of sound. You would then convert all the other consonants to digits based on their similarity. So B, V, P, and V, B, 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 those all kind of fit together. The harder, and all these things, right? Mostly about the ways that we would form our mouth to create these letter sounds, right? C and G don't have a whole, they're not used in all the same words, but they're close enough that they're the kinds of things you could mix up in certain ways. D and T, L is on its own, M and N are very clearly connected, R is off on its own in this particular Soundex algorithm, right? So the idea is you've converted everything into these clumps of digits that are related to one another. And then you collapse them. So if I get a lot of C and K, right, that's one sound. And then ultimately, we actually remove all of those soft consonants and vowels so that we end up with a short string that is the first letter and then the string of digits representing a cluster of the consonants, the consonants that you hit on your way through the word. So let's look at some examples of how to apply this. Cat and code. Okay. We would say, we would keep the C, right? We would convert the A to a 0, and then we would add a T. The T would become a 3, right? So CO3. We remove all of the zeros, and then we pad it out. C300. How about code? Well, C03 again, because D and T are in the same category. And then the E becomes a 0, C030. But again, remember, we remove all the zeros and pad it out with zeros. So C300. Cat and code are in the same soundex classification. So this soundex will point to both cat and code. It's not a perfect match, right? Cat and code are quite different words, but they have at least enough physical features in common that you would see, oh, these have a hard T or D sound. They start with a C, and then the rest is vowels. How about here and here? This one is a big one, right? Here, the vowels become zeros, and the R is a 6. H600. Here, again, but the vowels are zeros, and the R is a 6. H600. Here and here, they have the exact same soundex. Rupert and Robert. Those also collapse together. And there, and there. Let's do those common ones. T0060 down to T600. T00060 down to 600. 600. So the idea is that we've come up with a way of smushing these long words into a reduced form that helps us capture about 4 syllables. About 4 consonant structures, clusters, in the word can be captured using this very basic soundex algorithm. And it helps then, you can select things that are close. So, again, this is a simpler process than the previous ones. The idea is you would just build a soundex term index, right? So every soundex, once again, you can convert your search into soundexes, just like you can your query into soundexes. But it makes it possible to do this kind, right? So these are not simple lexical errors of typing. These can be kind of more broader errors that you're like, oh, that I heard the word correctly, I just never knew how to type it, right? So quite useful. This one's a little more fun. It's not as like intense. You don't have to do as many processes. It's just building the soundex index once and then a very small index. But it allows you to do this second kind of correction. It's really not all that difficult. But you'd still have to employ the same kinds of rules for, I'm only going to run things through this if I get like almost no findings or I get very low amounts of findings, that kind of stuff. So that brings us to the end of this deep dive into 2 very interesting processes for helping the user out. Spelling correction lets us correct these typographical errors using this multi-step algorithm to find and compute the nearest term. And then phonetic correction lets us correct for phonological errors by encoding words in this soundex form that helps to capture their spoken syllable structures. Both of these add cost, right? They both make it so that it's going to take a lot more processing oomph to get an actual option out. But they can also be used reactively to help the user. So you don't have to necessarily always process every term like this, only if they really miss the mark with their first try. Okay. That brings us to final thought. Besides spelling and phonetics, what other forms of helpful corrections do people use in everyday interaction? Do you imagine we could achieve those forms of correction using any of the indexing techniques we've covered? All right. Thanks, and take care.